So let's say this is a positively charged plate. Let's say plus sigma, where sigma is the charge per unit area. And we have some vacuum, which is a dielectric material or insulated material, separating this plate from this other plate, which we now have negatively charged. In reality, these plates are not infinitely large. In reality, you could say that the total charge on this plate is plus capital Q. The area of it is A. And for the other one, the total charge on this is minus capital Q, and its area is also A. So that the charge per unit area on this plate is simply Q over A. It's the total charge over the total area. That's the charge per unit area. And the charge on this, right, is going to be also like minus Q over the area. And let's separate these two plates by a distance D. Now, we solved this problem already. I mean, what do we know about this problem? We know that the electric field is non-zero where? Middle. In between them, correct. In the middle region. So there is an electric field between them. And it points from where to where?
Left to right.
Left to right, from the positive to the negative charge, right? So there is an electric field in here, right? That's not equal to zero. In fact, do we know an expression for the magnitude of that electric field vector?
Sigma over epsilon naught.
Correct. It will be the charge per unit area on either plate, right, divided by epsilon naught. And notice that that's independent of position. So this electric field is uniform. Because the electric field is uniform in the region separating these two plates, there is a potential difference between these two plates. Not so good. So there's a potential difference between these two plates, delta V. So we could say that the potential on this plate is V plus, and the potential on this plate is V minus. Which of those two plates is at the higher value of electric potential? The positively charged plate or the negatively charged plate?
Positive.
The positively charged plate, correct. So if I write this as potential difference as V plus minus V minus, that's going to be a positive number. And what is the relationship between this potential difference, the magnitude of this electric field, and this separation distance between the two plates?
Delta V equals electric field times distance.
Correct. Correct. Right, we have that. Now notice that the electric field can be written as, in fact, I'll say this, but E equals sigma over epsilon naught, which means that since the charge per unit area sigma is Q over A, I can write this as 1 over epsilon naught and then Q over A. Correct? And if I take this expression and I plug it in here, the potential difference between these two plates becomes Q over A epsilon naught B. And it means that I can write this equation, Q, that Q is the magnitude of the charge on the plate, right? Plus Q minus Q there, so it's just the magnitude of the charge on either plate. This equals A times epsilon naught divided by T, right, times delta V. Correct? I haven't done anything new yet, right? All of this is stuff that we learned in chapters 22 and 23. Yes?
If you could explain why that equals to sigma over epsilon naught.
Gauss's law. If you have one sheet the electric field is sigma over 2 epsilon naught. And the positively charged plate generates over here sigma over 2 epsilon naught, but the negatively charged plate generates an electric field towards it, also sigma over 2 epsilon naught. You have the 1/2 and the 1/2 and you get 1. So that comes from Gauss's law. We did that in chapter 22. Now notice the following. Notice that I can write this like that. And notice that this parameter over here, which is a proportionality constant between the magnitude of the charge on either conductor and the potential difference between the conductors, it's this quantity, right? That's the proportionality constant. And this quantity only depends on what? It depends on how big the area is of the conductors, on how far away the two conductors are from one another, and on some electrical property of the dielectric material between them. So that's called the electrical permittivity of free space, the electrical permittivity of vacuum.
Will we eventually change epsilon naught to different values, like depending on what? No, it's always going to just be a vacuum.
I mean, the other, if you see it in like 4 pi epsilon naught, then 1 over that, it's, you know, it's 9 times 10 to the 9th, right? Coulomb's constant.
Mm-hmm.
But
Okay.
if I don't see it like that, if I see that combination, then I may, instead of writing all of this, it's just easy to write Coulomb's constant.
So capacitors are always going to be with the vacuum. There's no
Yeah.
other. Okay.
So if I replace epsilon naught, by 1 over 4 pi k, and I wrote this expression, Q would be A times over 1 over 4 pi k, and then I have a D, and then a delta V, right? So, actually, hold on, that goes downstairs, so that would be 4 pi over here. Because 1 over epsilon naught is 4 pi k, right? So if since it's upstairs, no, it was good, right? It was good. Okay. But this is simpler. I still have A and D, but now I have 4 pi k when I just have epsilon naught. It's just easier to write it like this. But either way is good. Either way is good. So, what this equation says is the following. Suppose the area is given. You know, you have a plate with a certain area. Suppose the separation distance is given. Some distance given, right? And epsilon naught is just a constant, right? Epsilon naught for vacuum, this is 8.85 times 10 to the minus 12. Right? So, if you know the area of these plates and how far away they are from one another and the type of dielectric material in here, insulating material, then all of this is just a number. For the sake of argument, just for the sake of argument, because this number is very small, suppose, just for the sake of argument, suppose that given the area, epsilon naught, and the distance, suppose that this comes out to 3. Let's just suppose that you evaluate, you give me the area of the plate, you give me how far away they are from one another, include epsilon naught, and you get 3. Right? What this equation says is that the magnitude of the charge on these plates is 3 times the potential difference between the two plates. It is a relationship between the charge, the magnitude of the charge on either plate, and the potential difference between the plates. And that A epsilon naught over D, that 3 is just a constant. It's just a proportionality constant. So all it says is the following. Suppose that for this capacitor, for these two conductors separated by this insulating material, for that capacitor, if we have this, right, and I ask you, okay, what will be the magnitude of the charge in either plate, right? If I tell you what the potential difference is between the plates. Most this is in volts. Let me make myself more room over here. Suppose I tell you if the potential difference between the plates is that many volts, and what will be the charge in coulombs? And this is 3, and this will be volts per coulomb. If I tell you that the potential difference between these two plates is 0, then what's going to be the charge on either plate? 0. And does that make sense? Should it be 0? Should it be 0 because of this expression, or should it be 0 also because of something else? See, if the potential difference between these two plates is 0, what can I say about the electric field in this region?
Also zero.
So what would it be? What does it have to be? If notice, right? So there's physics in here, right?
If the charge.
Let's not lose the physics because of this simple equation over here, right? I just asked you if the potential difference is 0, what's the charge? And then you probably did 0 times 3 is 0, right? Now let's think about that physics-wise, right? If the potential difference between those two plates is 0, what do I know about the electric field between those two plates? What does it have to be?
0.
It has to be 0. Well, in fact, you see it right here. If the potential difference is 0, the electric field has to be 0. And if the electric field is 0, then there are no charges producing that electric. There's no electric field to be produced. There are no charges there. If the electric field here is 0, that means there has to be no charges over here. Because if there are charges, one plus in one, negative in the other one, there is going to be an electric field. So if the potential difference is 0, it means the electric field in that region is 0. And if the electric field is 0, that means that the charge field area is 0, which means the plates are not charged. Which is what this is saying, right? Yes? Okay. What if I tell you that I'm going to make the potential difference between those two plates equal to 2 volts? Now, what will be the magnitude of the charge on either plate? Plus Q in one, negative Q in the other one. What will be the charge? Now, you can do the math. 6 coulombs. Then you would have plus 6 coulombs here, negative 6 coulombs over there. What if I tell you that the potential difference between these two plates, right? In other words, they're charged. And because they are charged, plus minus, there's an electric field. And there is a potential difference between them. And I tell you now that the potential difference is 10. What can you tell me, therefore, is going to be the charge on either plate?
30.
30 coulombs. Plus 30 in one plate, negative 30 in the other plate. Yes. So, this constant of proportionality, this one, right, which I just made it equal to 3 for the sake of argument, right? This constant of proportionality, notice, it's a constant. What needs to change in order for this quantity to change? I need to make the area of the plates bigger, or I need to change the separation between them, or I need to put a different insulating material between the two plates. Right? If this is kept the same, that's determined by the geometry of this thing, right? By how big the areas are and by how far away they are, and also by the electrical properties of what separates those two conductors. This constant of proportionality is called the capacitance. And for the case of the set of parallel plates, is the area of the plates times epsilon naught divided by d. That's the capacitance of this set of parallel plates. And by the way, this will be in units of volts per coulomb, but a name has been given to the units of this quantity. In units of, anyone know? Farads. after Faraday, after Michael Faraday. So farads.
I have a question.
Yes.
In chapter 23, we were given Q and we can calculate delta V, but when we given that Q equal to whatever number to delta V, we transfer back to delta V.
Can we what?
Like, for example, that table, when you were given Q, we just.
Yeah, like I did over here, like you give me Q and the area, then I know sigma, the charge between area, and if I know sigma, I know the electric field. And if I know the electric field in this distance, I know the potential difference. The question is, can you tell me right away what that charge is if I only tell you the potential difference? Because what I did over here is this. I told you, these are charged, plus Q, minus Q, right? And then I say, okay, they're charged. The plates have an area A. They're separated by a distance D. There's vacuum between them. And then if I go straight to the question, what if the potential difference between these plates is 2 volts? What's the charge in each one of them? So what you can do is say, okay, if the potential difference is 2 volts, right? If the potential difference is 2 volts, from this expression, I can figure out the electric field. And once I know the electric field, I can plug it into this expression and I can figure out the charge per unit area. And since you gave me the area, I can figure out the total charge, Q. But if I give you the potential difference, right, and I ask you for the charge on each conductor, from the potential difference, you gotta first find the electric field. From the electric field, you find the charge per unit area, and from the charge per unit area, you find Q. That's 3 steps. But so it could be done, that's, you know. But if I know the capacitance of it, and you tell me the potential difference is 2 volts, then right away I can tell you what the charge is under the plate. That capacitance is the constant of proportionality, right? That connects the potential difference between the 2 conductors that makes up the capacitor and the magnitude of the charge on either conductor. I want you to think about it like that, and notice that this capacitance, this quantity over here, is a purely geometrical quantity. Right? This is purely geometrical. Why? Because it depends on how big the areas are of these conductors. It depends on how far away they are from one another, and it also depends well on the electrical properties of the insulating material that separates those 2 conductors. And I say this because of the following. So, the definition, the way that you normally see capacitance, defined as is like this. So, that's the capacitance in this case. So the way you say it is Q equals C delta V. And so oftentimes you see the capacitance written like this. Right? It's the same equation as this, right? C is Q over delta V. Yes? No, I just made it up. I said, suppose. I made it. I mean, in reality, if you give me the area, the separation distance between them, then I gotta multiply that by 8.85 10 to the minus 12, and I'm gonna get some number with decimal places and 10 to the minus something. I just wanted to have the discussion so that if I tell you the value of the voltage or the potential difference between the plates, right away you will be able to tell me what the charge is without needing a calculator. But capacitance is oftentimes defined like this. And there is an entrance exam to medical school. You know, you finish your bachelor's degree, that's your 4 years of college, right? And then if you want to go to medical school, you apply to medical school. It's a different school. And, you know, you submit letters of recommendations, you submit your transcripts, you write a personal statement, and you take an exam, an entrance exam to medical school. It's called the MCAT. And in the MCAT, they give you a passage with some information, and then they ask you questions. And when, in an MCAT exam, in a previous MCAT exam, there was a passage on capacitors. And then they said, it's two conductors separated by an insulator. If the magnitude of the charge on either plate is Q and the potential difference between them is delta V, the capacitance is given by that. Right? And then they hit you with the first question. If the charge in the plates is 0, what's the capacitance? Suppose the charge in the plates is 0. What's the capacitance? And you're looking at that expression, and what do you want to say? Maybe, I don't know, maybe.
We want to say Q,
Undefined.
right?
What do you think is the wrong answer?
Q.
No. So, if the question is, if the charge in the plates, in the conductors, is 0, what's the potential difference? I'm sorry, what's the capacitance? So, if this is 0, what's the capacitance?
0.
And that's wrong.
Remain the same.
What's that?
Remain the same.
But what is it?
Is
A epsilon not over D.
That's right. But it is not 0. One of the choices, you may have 4 choices, and the choices are never, I think, none of the above. It's the answer is in there, right? And one of the options is 0. And a lot of people choose 0. Because they say, oh, if there's no charge, this has to be 0. Period. But what's wrong with that reasoning? It's the wrong answer. 0 is not the right answer. What is wrong with that reasoning? Yes?
Capacitance doesn't have a dependency on the charge, it has that dependency.
So you have to remember that. Yes. But if somebody says, wait a minute, what do you mean C is not 0 if Q is 0? I mean, I look at that and C's gotta be 0 if Q is 0. What's wrong with that?
It's not like the capacitor doesn't exist anymore. It's just there's no charge running through it.
But if I look at the mathematics of that, what's wrong with that? What's wrong with me concluding that C is 0? I mean, they tell you about the capacitor, right? And then they show you this formula, right? And then they ask you this question. Suppose the charge in the capacitor is 0. What's the capacitance? And a lot of people, and an option, or not an option, one of the choices is 0. And a lot of people say, oh, if the charge is 0, C is 0. Yes?
I mean, isn't C just like the area, the constant, and then over the distance? So why would that be 0 if it's physical? Like,
Good, but I'm saying that's correct, right? It's the capacitance doesn't depend on the charge, right? The capacitance is a purely geometrical quantity. It depends on how big the thing is, how far apart the conductors are that make up the capacitor. It depends on what's between the two conductors, right? And that's going to be some number, which is not going to be 0. But what's the problem?
I was going to say, so shouldn't the caveat for that definition be as long as Q is not 0?
No.
No? Okay.
So it's a trap. No, you don't see. I mean, is this true? If Q is 0, then C is 0? Is that true?
No.
How do you know is that true? Suppose I had not told you anything about capacitance. Or maybe not much. Then what?
Because if delta V is also 0, then it's undefined.
Exactly. If you think of this equation like this, I'm just going to rewrite it. Q equals C delta V. This is not going to be 0 because that depends on how big the thing is. So if this is 0, what that means is that this guy has to be 0, the potential difference. And that makes sense, right? Because if there is no charge between, and those plates, plus or minus, there's not going to be an electric field. And if there is no electric field, there's not going to be a potential difference between them, between the plates. Right? So actually what happens is that if Q is 0, what that really means is that delta V is 0. And C could actually be anything, which will just depend on the geometry of the thing, right? So the wrong conclusion is to say, oh, if Q is 0, but this is how they give you the equation in the MCAT, right? They don't even write it to you like this. So they write it like that, and then they just want to know if you know that capacitance is a purely geometrical quantity, and it has nothing to do with the voltage, it has nothing to do with the charge. It's just, I give you this capacitor, suppose I tell you, here's this capacitor, here it is, right? And the value of its capacitance is 5, right? What that means, and that 5 is determined by the area of the plates, the separation between them, the stuff between the two plates. Let's say you get 5 farads, right? All that means is that for any potential difference that you give me between the two plates, I can tell you what the charge of the plates is equal to, or vice versa. Give me the charge and I'll tell you what the potential difference is right away. So 0 charge means no potential difference. It doesn't mean the capacitance is 0. So it's like a trick question in the MCAT exam. Either you know it, that it's something that depends on the geometry of the thing, or you fall in the trap that they set up for you.
So I'm assuming in the rest of the question they gave you the geometry of the, then,
Or maybe they'll say, suppose the capacitance is this, and then they ask you
Oh,
other questions on how much energy is stored in it, and there are other questions that could be asked. What's the charge if the voltage is this, but they hit you with the first question with that, and then it's like, oh, no, gee, if Q is 0, then C has to be 0. But no, that's not what happens. Actually, if Q is 0, there is no charge in the plates, there's not going to be an electric field. And if there is no electric field, there's not going to be a potential difference between the plates. So 0 charge means 0 potential difference. And that means that C can be anything. Well, it's whatever it is, determined by the geometry of the thing. How big it is, in areas, right? Each conducting material, each of the two conductors, the area of each conducting material. By the way, that area, let me say something about this area. Because you could have one of these sheets like this, and the other sheet could be this. In fact, this other sheet could be in position like this. So in this expression, the area that you want, right, is actually put them overlap, is the area between them. Right? So it's like I have this plate, if I put it like this, well, it's the area of each palm. But if I put my hands like this, it's the area between them. Not including this area, not including this area, it's the area between them. Right? So you can change, so we'll learn later on that capacitors are also used in electric circuits. And these are connected to resistors and batteries and so on, right? And then there's a resonance frequency for this thing to respond to voltages applied to it and so on. And you can change the resonant frequency of the capacitor you can change the capacitance by changing the area of the area between the two plates. Those older radios that have a dial, a knob, and then you go like this, right? Oh, I want to tune into 102.7 or 103.5 or whatever. When you turn the dial, there's a plate in the radio that's fixed, and when you turn the dial, you're turning another plate. And as you turn this plate, the area between them is changing. So what you're doing is you're changing the area, the effective area between the two plates, and you're changing the capacitance. And by changing the capacitance, you can tune into another, frequency of electromagnetic wave coming in. Right? So that dial is that you turn. You're physically turning one plate. The other one stays fixed. So you're changing the area between them. But anyway, what if you have, I think I did it in my notes, what if you have a capacitor like this? Spherical capacitor, I think I called it in my notes. So the first thing is purely geometrical quantity. In what units is it measured? In farads, after Faraday. You know, volts. Volts, the unit of potential difference, is after Alessandro Volta. So, you know, they dropped his last letter in his last name. So it's volts. So Faraday, so they dropped the A by Faraday. Coulombs, I guess they could have said, you know, oh, the unit of charge is the cool. But no, they kept his name. Newton, they didn't say, you know, a force of 5 newt. No, it's newtons, right? So they kept the name Newton. Anyway, and the unit of magnetic field in the metric system is Tesla. There's also another unit of magnetic field in another system of units, which is the Gauss. But you know, those are, they didn't drop any letters in the last names of those peoples. Inductance is mentioned in Henry's, somebody else's last name.
So
What
these
about
people got
ohms?
ripped off.
What about who?
Ohms, like
Somebody's last name.
That is?
I think it's Charles Ohms. It wasn't Ohm or something else. It's actually Ohms, I think. Amperes is the unit of electric current, but they shortened it to
Amps.
amps. 5 amps. Amps?
What
Amps?
about watts?
No, watts is somebody's last name too. I mean, complete
Wasn't watts.
last name. But amps is really, it's amperes from, you know, some French guy. And so they dropped the E-R-E-S at the end, amps. So people just used to say amps.
Is Jules somebody's last name?
Jules, somebody's last name too. I think Charles was his first, I don't remember his first name.
Is it gonna be a Guerra?
Then they'll call it Guerra. Or something like that. Okay, let's consider, let me put it up. I think I have a spherical capacitor in there.
Here's my back.
Let me do, that one is the one that I just did, right? Except that I just pulled the results. I mean, I did it officially. I could have just gone straight to delta V equals ED, right? And then notice, purely geometrical, right? What if we have a spherical capacitor? This one is a parallel plate capacitor. What if we have how about a spherical capacitor? What is the capacitance of a spherical capacitor? So what do you have? Well, remember, capacitor, 2 conductors are provided by some insulating material. So you can have 1 conductor, you know, a solid sphere of radius A, so this is a metal. And then you have vacuum. And then another, you know, thin spherical shell. Very thin. This is like a thin spherical shell. And that has radius B. So what is the capacitance of that? So the capacitance will be, well, the magnitude of the charge on either conductor divided by the potential difference. Now, remember, this result depends on the geometry of it. So it's not gonna, in the end, I'm not gonna have a charge Q in my expression. I'm just going to say if, for example, if I charge the inner conductor with plus Q, then the charge on the outer conductor is minus Q. Right? For capacitors, it's always one conductor is positively charged and the other one is negatively charged with the same amount of charge, but negative, right? So I'm going to give these conductors one plus Q, the other one minus Q. And then that means that there's a potential difference between them, between those two conductors, right? So what I'm going to do is, having given these conductors this charge Q and minus Q, I'm going to find out what the potential difference is between them, and then I'm going to use this formula, and what I'm going to get will have nothing to do with these charges and this potential difference. It'll have nothing to do with that, which is how I'm going to get started, but then in the end it's going to disappear. In fact, you can see what the answer is. Notice that the answer depends on 4 pi epsilon naught, that's some electrical property of the material separating the two conductors that I said vacuum between them. The radius of one of them, the radius of the other one, the difference in the radii of them. You know, something just geometry. That's the result that we get. But how do we get that result? I will think that this is charged, this one is oppositely charged. I find the potential difference, and then I take Q divided by the potential difference, and that'll be my answer. But in the end, it doesn't mean that I need to have charge in these conductors in order for there to be a capacitance. If there's no charge in this conductor, the potential difference is going to be 0. That's what that means. The capacitance is something. It's just that I'm going to put it in there, but then you'll see how it'll cancel out. So, starting with this, it's the capacitance will be Q divided by, well, what is the potential difference between these plates? I mean, between these two conductors. These two spherical conductors. One of them is solid, the other one is thin. Well, do we know how to calculate potential differences between two, spheres like that? We learned that in chapter 23, right? The way you find the potential difference is you say, okay, I want, which of these two conductors is at the higher potential? The potential of the conductor with radius A, or is it the potential of the conductor with radius B? A. Good. How do you know? Okay. And it also means that in the region between them, there's going to be an electric field pointing this way, right? Away from the positive charge towards the negative charge. And if you walk in the direction of the electric field, the potential gets smaller. So therefore, I'm going to just give a potential of V sub A. That's the potential at radius A. That's the electric potential on the surface of the inner conductor. And I'm going to say that the potential on the surface of the outer conductor is V sub B. I'm just giving them names. So what is delta V going to be equal to? It'll be just VA minus VP, right? Yes? It's just a difference in potentials. Well, how do I get this quantity here, right? Isn't this equal to? Are you ready for this? Can I say that this is equal to the integral of dV from VA? Well, integrated from VP to VA. Right? Is this equal to this? Yes, right? But what is? And this equals, and then I'm going to just copy the limits of integration. That's B. But what is this? We know that dV is minus EdR. Right? So then I take that and I bring it in there. So this would be minus EdR. And this is the electric field in the region of space between radius, at B and at A. If you don't like that minus sign over there, we can flip the limits of integration. So this would be V at A, V at B. Now, this means that I have to know what the electric field is I made a mistake. What was my mistake? I'm integrating with respect to R. So this limit should be B to A, right? Not, it was VB, VA over here. So this has to be B to A. Please correct me when I make mistakes like that. And then this didn't make sense. Now, this is the electric field.
Once you flip, shouldn't it be B to A?
No, I was
You flipped integral by getting rid of the negative?
over here. From here? Oh, to here, right? Thank you. So this is why I don't like to do it all in the same line. Thank you very much. And this E is the electric field in the region between radius A and radius B, which is where? That would be between radius A and radius B. I want the electric field here at a distance R. How do I find the electric field over there? Gauss's law, right? So I draw my Gaussian surface, and I can just do it over here, right? E times what? What do we multiply E by when we use Gauss's law? The area of the Gaussian surface, which is, what should I say? 4 pi A squared, 4 pi B squared, 4 pi R squared. What should I write down?
R
R squared.
And I need to include in the right-hand side of Gauss's law the total charge inside my Gaussian surface, right? What is the total charge inside my Gaussian surface?
Q positive.
Just the charge in the inner metal, right? Capital Q. Yes? So the next line is the electric field. So this is 1 over 4 pi epsilon naught, which I can combine that into a K if I wanted to, so I wouldn't have to write so much. And this is Q over R squared. And that electric field goes in here. So instead of K, if I write it as KQ over R squared, so I don't have to write 4 pi epsilon naught. I'd rather just write K than 4 pi epsilon naught. One letter as opposed to 3 quantities. KQ is a constant, right? And what is this integral equal to? From A to B?
Negative
What
1
is,
over R.
what's that?
Negative 1 over R.
Exactly. So this will be KQ. And I'm going to flip this, so this will be 1 over A minus 1 over B. And I can clean this up if I wanted to. This would be KQ B minus A over A times B. So therefore, the capacitance, now I take this and I plug it in here, right? The capacitance becomes Q divided by that potential difference, right? And what is that potential difference equal to? That potential difference, I just went straight along the board. That potential difference is this. So I divide by KQ B minus A over A times B. And notice how conveniently the Q drops out. We don't need to have the conductors charged for there to be a capacitance. So this will be A times B, and this is K, B minus A. Just, purely. Geometry. And K, Coulomb's constant, is associated with epsilon naught, and that has to do with the vacuum that I put in here between these two plates. Anyway, I think there's a cylindrical capacitor example that I did in my notes, in my lecture notes, so you can look at that. notice that we're applying what we learned in chapter 22, because you gotta use Gauss's law to find the electric field, calculate the electric field, and then plug it in here into chapter 23 to get the potential difference, so that then you can use this formula from chapter 24. Right? So we need 22, 23 to get something in 24. Okay? Anyway, that's just one part of this. What I am actually more interested in is in taking these two conductors, separated by an insulating material, and making them part of an electric circuit. So let's talk about that. How much time do we have? I always forget.
Till 5:30.
5 minutes.
Till 5:30.
Oh, until 5:30. Okay, so let me just set this up. I remember that when I first started learning about capacitors, I was overwhelmed with the expressions, the number of them, and so on. And at first you start memorizing stuff. But it's important to try to understand the physics as well, as much as possible. So, what if I have two plates, right? And this is one plate sticking out of the board, and here's another plate. And they're conducting plates, right? And let's say we have some dielectric material between them, or some vacuum, or they're separated. There's some, not a metal between them. No, they're two metal plates. And I connect a wire to this plate and another wire to this plate. So let's analyze this simple case first. And then I have a battery here, a DC battery. And the DC battery has a positive terminal and a negative terminal, right? You measure the voltage of a DC battery that I gave you. Some of you measure 1.6 volts, others measured 9 volts, others measured 6 volts, depending on the battery that I gave you, right? And this is just a wire, right? A conducting wire. Same thing over here. These are plates, metal plates. Right? And I take this wire and I connect it to this terminal of the battery, and this one to this terminal of the battery. So what's going to happen? The battery will establish an electric field in these wires. Okay? What will be the direction of the electric field over here in this piece of wire? Which way? Okay, so this way, right?
Yes.
What about the electric field on this piece of the wire? Right, correct. What about on this piece of wire?
The right.
To the right. What about over here? Right, towards the negative one, right?
Excuse me.
So, yeah?
Because it goes from positive to negative, does the electric field switch inside of the battery?
Actually, there are other electric fields in there, but it's
Because it looks like it would go opposite where it is on the wire inside of the battery.
but there's something in there also that creates an electric field inside. And actually, inside the battery, there's more stuff in there, so it's kind of like this also, overall.
Okay.
Because there's some chemicals in there and so on that are used to separate charges at these terminals over here, so it's kind of complicated in there.
Okay.
What I'm trying to get at is this. What does this wire have that can move around?
Free electrons.
Free.
Electrons, right? It's got electrons. And an electron over here, well, it's negatively charged, right? So it'll experience a force exerted by this electric field in which direction? Up the hill or down the hill?
Up the hill.
Up the hill. Remember, F equals QE, right? If we're talking about an electron, the electron is negatively charged. So the force that it will experience will be in the opposite direction to the direction of the electric field that that electron is sitting in. So the force on this electron is going to be this way. And the force on an electron over here is going to be this way. Right? And so what will happen is that electrons are going to then move counterclockwise and they'll begin to pile up over here. And what are those electrons going to do to the conduction free electrons on the other plate that's across it? They cannot go through it because there's no metal connecting this plate to this plate. But it will do what to them? Pull them or push them away?
Push them away.
Push them away. So what will happen is that, or you can say this, there's another electron here, right? And that's going to be pushed away. And as the electrons are pushed away from this plate, there will be an excess of positive charges left there. And then these electrons, will go this way. The force on the electron, right? In other words, what will happen is that there's going to be a flow of electrons in the counterclockwise sense in this circuit. But as electrons pile up over here on this plate on the right, what are they going to do to the other electrons that are coming in? Repel them. And it will say like, stop, there's no room for you over here. Right? Yes? And so what will happen is that, and this positive charges over here will push away electrons also from here, right? And so what will happen is that eventually the charge is going to, the flow of electrons is going to stop. Because you will have accumulated so much over here, right? So, and remember, if now this will become negatively charged, let's say whatever it is, minus Q, right? Now, if, 15,000 electrons arrive over here, 15,000 electrons left the other one, the other plane. So then the charge in this will be plus Q. And now you have two conductors separated by an insulator that's charged. And because of the area of these plates, right, the areas and the separation between them, these two conductors constitutes a capacitance with a given capacitor. A capacitor with a given capacitance. Yes? So what will happen is that if the voltage over here, let's say the voltage over here is 10 volts. When you make this connection, it will charge the capacitor, and the potential difference between these two will become 10 volts. And if I know the capacitance, I can tell you how much charge is going to accumulate on each plate. Because there's a connection between the capacitance, the charge on the plate, and the potential difference. So what I want to talk about next Tuesday, no, Monday, right? Is what happens if we do this? What happens if we have a battery and we put one set of plates like that and then a wire and we put another set of plates? And this one, the capacitance of that one is C1 and the capacitance of this one is C2. And they don't have to be the same, because, well, what if the distances between them are different? What if the area of this is different from the area of that? So they are going to have different capacitances, right? For this one, it will be epsilon naught A2 over D2. For this one, it will be epsilon naught A1 over D1, right? So if these areas and this separation distance between the plates are different, the capacitances are going to be different. And then I take this other one and I go like this. So what will happen is that this plate will become negatively charged. So, and this one positively charged. And we say that the charge on this is minus Q2, the charge on this is plus Q2. Now, the electrons that leave this plate, where are they going to go? To the left. So they'll pile up over here. And so the charge on this plate is minus Q1, and they're going to push away electrons from this plate, and the charge on this is going to be plus Q1. So electrons are going to flow this way. They're going to go through. They're gonna go like that until they fully charge themselves. And then what we wanna know is, okay, when it's fully charged, how much charge is this capacitor going to accumulate? And how much charge is this other capacitor going to accumulate? What will be the potential difference across this? What will be the potential difference across that? Given that maybe the potential difference across this is 10 volts. And so these two capacitors are said to be connected in series. Another way of connecting the two capacitors is to do this. You take the battery, plus, minus, and you can do this. That's one capacitor. And then you join this wire and this wire, and you put another, you make this other connection. So now you have maybe C1, capacitance C1, and this one C2. And this is a DC battery. Again, maybe 10 volts. So what will happen is that this will get charged. So, minus, 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 plus, plus, plus. So this will get minus Q1, this one will get plus Q1, this one will get plus, plus, minus, minus. So this will get minus Q2, and this one will get plus Q2. And we want to know, well, if we make this connection, what will be the charge on these plates? And what will be the charge on those plates? What will be this potential difference? What will be that potential difference? How is that different from this? And then what we want to do is, well, this is like easy. What if we have a battery like this? And then maybe I go like that, and I put a capacitor there, and I go like this, and I go like that. And then more wires.
That looks like a nightmare.
And I have various capacitances, and what's going to be the charge in this, what's going to be the charge in that, what's going to be the charge in this, that. What's this potential difference, what's this potential difference, what's this voltage, So, given a circuit with a DC battery and a whole bunch of capacitors, right? How do we figure out the voltage across every capacitor and the charge on every capacitor? We want to be able to do that. So I'm going to teach you that trick on Monday. It's kind of fun. It's really a lot of fun because as you solve the problem, there are ways to check if you're doing it correctly or incorrectly. And it'll be passing those checks. By the time you're done with the problem, it's like if I put a problem like that in the next test, you can check along the way, and you got your 15 points for that problem. So, it's kind of nice because I'll show you how we can check. We're going to figure it out and then check, figure it out, check. And in the end, it will be done and we'll be certain that our answers are correct. I'll show you how to check and how to actually do the problems. So, some of you came in after I had taken attendance, just let me know so that I can mark you present.
No, it's the week
So,
after.
have a good weekend, and some of you I see later,
This is
right?
week 7.
Now?
Yeah, at 6:45.
Yeah, I think I should.